Welcome to The Explainer. Today, we're diving into data pipelines, what senior engineers know that most developers don't. And listen, we are completely stripping away the fluff here. This isn't about shiny new frameworks or whatever's trending on social media today. This is about the brutal, unvarnished reality of operating massive, distributed systems in production. We're talking about the architectural decisions, the battle scars, and the absolute non-negotiable rules that separate systems that scale from systems that just crash. Let's dive right in.
All right, picture this nightmare scenario. It's Monday morning. A major competitor just dropped a massive new feature over the weekend, and they're gobbling up market share. Your team is scrambling to match it. You build the code, you push it through CI/CD, and your staging environment is perfectly green. Everything looks amazing. You hit deploy, and instantly, your production Redis cache is completely wiped out, gone. Why? Well, it's a classic case of leaky automation logic. A post-deployment script executing in your staging context accidentally used a hard-coded VPC peering endpoint connected straight to production. This right here, this is the difference between simply writing code and actually operating systems.
And this brilliantly illustrates the divide in how we approach infrastructure. You've probably heard the joke about the scream test, right? Where you just turn off a server and wait to see who complains? Let me be perfectly clear. In an enterprise environment, pulling a stunt like that is literally a career-ending move. Senior engineers, we don't guess. Before we ever touch a single server, we use network telemetry and cloud provider flow logs to build a mathematical, perfectly accurate dependency graph of every single byte of traffic in our network. Because visibility has to precede action, every time.
All right, let's get into Act 1, the junior traps.
So one of the most subtle mistakes I see all the time comes down to how we formulate hypotheses during an incident. When a pipeline is totally green in staging but completely failing in production with data errors, a junior developer almost always assumes a failed deployment or, random broken hardware. But as a senior engineer, I'm immediately looking at the data-to-code interaction. I suspect the synthetic data fallacy. See, your test suite uses mocks and fakes that assume ideal, perfectly shaped data and absolute zero latency network conditions. Production, on the other hand, has messy, poisoned data and very real-world latency. The failure is almost always hiding right there in that mock-to-reality parity.
Okay, here's another classic trap, Docker image tagging. Using that latest tag? Yeah, it seems super convenient, but it's actually a massive security and auditability risk. It's basically a rolling pointer. If a pod restarts, you have absolutely zero guarantee it's pulling the exact same code that was running just 5 minutes ago, which makes rapid rollbacks impossible. Seniors implement strict tag immutability. We force specific, hard-coded version tags. And actually, if you're worried about registry storage costs skyrocketing because of this, don't be. We just implement lifecycle rules to auto-delete images older than 90 days. We will happily trade cheap storage costs for absolute deployment safety.
Now let's talk about a silent killer that absolutely destroys pipelines, the N+1 query problem. This happens when your code executes one database query to fetch a list of items, and then turns around and executes an additional query for every single item in that list. It's incredibly dangerous in modern GraphQL applications that use those highly flexible nested structures. Seniors fix this at the architectural level. We use data batching tools like Data Loader to group all those requests into a single execution, or we utilize pre-joined database views to just eliminate the N+1 load entirely.
Moving right along to Act 2, Scalability and Performance Trade-offs.
When you're designing for scale, you have to realize that everything in distributed systems is a trade-off. It all comes down to choosing the right caching strategy. Cache aside, that's your reliable default. If the cache fails, you just fall back to the database. Simple. But look at the write-behind pattern. It gives you insanely fast write performance and massive throughput by saving to Redis first and then asynchronously updating the database later, which is brilliant for telemetry and logging. But if Redis crashes before that sync happens, you experience total, irreversible data loss. Using write-behind for a payments or order processing system would be an absolute architectural catastrophe.
We also see these trade-offs defined perfectly by the CAP theorem. In high-traffic e-commerce systems, you'll constantly see architectures intentionally prioritizing availability and partition tolerance over strong consistency. So, what does that mean in practice? It means we are totally willing to accept temporary data inconsistencies, like maybe showing you slightly out-of-date inventory numbers just to ensure a user never ever experiences a blocked checkout during peak load. Eventual consistency is simply the price we pay for continuous uptime. But what happens when we need to push performance to the absolute limits, like in ultra-low latency financial trading? That's where we apply mechanical sympathy. We design software that plays nicely with the actual physical realities of the CPU. By using patterns like the LMAX disruptor, we intentionally trade dynamic queues for fixed-size ring buffers. We vastly prefer single writer designs to completely eliminate thread lock contention. And we intentionally pad hot memory fields to avoid CPU false sharing. Why go through all this trouble? Because the cost of some wasted RAM is far, far cheaper than the cost of unpredictable latency spikes in a high-frequency system.
Which brings us to Act 3, building resilient data architectures.
Building true resilience really starts with how we handle live state. Look, making structural changes to a live database is literally like performing open-heart surgery while the patient is running a marathon. You cannot just wing it. You absolutely must use the three-phase migration pattern: expand, migrate, and contract. First, you add the new columns and write to both the old and new locations simultaneously. But here's the catch. You risk massive application-level split brain if your logic is buggy. So you have to run data reconciliation scripts to verify perfect parity before you ever even think about moving to the contract phase to drop the old code.
And speaking of migrations, here is a hard, non-negotiable rule: the pre-flight row count. Before running any migration, you run a simple count query on your target cable. If the count is over 500,000 rows, an automated SQL alter statement will almost certainly lock the table for too long. Any table this size requires explicit senior architectural sign-off and the use of an online schema change tool, like Ghost. These tools use ghost tables and atomic swaps to basically update your schemas without ever locking out your users.
Now, take a look at the data here on service failures. It completely shatters conventional wisdom. A staggering 72% of failures in online services actually originate in the front end or from operator errors, not the back-end hardware. Operational observability, meaning having exact runbooks, knowing exactly what a deployment script is doing at all times, and preventing human error, is vastly more critical to keeping your pipeline up than just throwing money at more expensive hardware.
So, to combat those operator errors, we implement strict ironclad CI/CD guardrails. We enforce zero downtime policies, meaning no table locks longer than a second. We require all operations to be idempotent, so a script can be safely rerun if it fails halfway through. We strictly separate schema changes from heavy data backfills, but perhaps the most crucial rule of all is network isolation. Never, and I mean never, perform an external API call inside a database transaction block. If that API hangs, your database connection hangs in an idle in-transaction state, which holds locks and will completely destroy your database performance at scale.
All right, let's wrap things up with Act 4, the ultimate senior flex: strategic deletion.
We call this the deletion paradox. It's fascinating. A junior developer joins a team, adds 50,000 lines of code in a year, and their contribution graph looks like giant mountain peaks. Then, a senior developer joins, and in their first month, they delete 15,000 lines of code. They rip out unused microservices. They drop bloated dependencies. They simplify convoluted logic. Their graph looks like a deep valley. But guess who the organization values more? Your value as an engineer is actually inversely proportional to the amount of code you write.
Because, and this is a tough pill to swallow for some, the reality is that every single line of code is a liability. It is not an asset. Every new line creates more cognitive load for the next person who has to read it. It introduces new dependencies. It represents future maintenance debt just waiting to break when requirements inevitably change down the line.
Always keep this 10x rule in the back of your mind. Every line of code you write will be read 10 times, modified 3 times, and debugged twice. That is exactly why unnecessary abstractions, those just-in-case features we all love to build, and premature optimizations must be ruthlessly hunted down and eliminated. Simplicity beats sophistication every single time.
And hey, the results absolutely speak for themselves. The sources for this explainer detail a scenario where a team took a super convoluted 3,000-line configuration system and slashed it down to just 200 lines. The result of that deletion? An 80% drop in bug reports and a 40% boost in overall system performance. The absolute best code is the code that simply doesn't exist.
Ultimately, performance and resilience, they're properties of your entire distributed system, not just some isolated function. So I want to leave you with a challenge today. Go review your own pipelines. Look for those hard-coded endpoints, the hidden N+1 queries, the bloated dependencies weighing you down. Embrace that senior mindset. Decouple your systems and ask yourself, what code can you confidently delete today? Thanks so much for joining me on this explainer, and I'll catch you in the next one.